All right, good morning, you guys. Today we are heading into sampling distributions of a sample proportion. So first, just a little recap of some content from first semester. So we note that information derived from the sample is used to estimate the truth about the whole population. The process of drawing conclusions about a population on the basis of sample data is called inference because we infer information about the population from what we know about this sample. So our population, again, this is just a refresher. Our population is the entire group of individuals about which we want information. Our parameter, P, is a number that describes the population. It's a fixed number, but we don't always know its value. Sometimes we talk about it as the population proportion. So the proportion of the population that feel a certain way about whatever issue we're talking about. Our sample is a subset of the population. It's a part of the population from which we collect information used to draw conclusions about the larger population. So ideally, it was obtained at random, right? It should be representative of the larger population. And our sample is just information from concrete individuals, right? It has to be information that we've actually already gone out and obtained. Okay, our statistic, that's the P with that funny little hat on it. So that is a number that describes a sample. And we often use a statistic to estimate, to predict an unknown population parameter. So we often think of our statistic as our sample proportion. Okay, so it's the proportion of our sample that feel a certain way about whatever issue we're talking about. So remember that we keep the P's together, we keep the S's together. So parameter is to population, just like statistic is to sample. And again, this whole top part here is just a first semester recap. Okay, and example one, also a little review. So here we go. Prior to the 2016 election, a national poll interviewed 1,000 registered voters by phone. They were asked, if the election took place tomorrow, would you vote for Hillary Clinton? Of the sample of registered voters, 600 said yes. So what is our population, right? What is the whole group that we are interested in knowing about? We're interested in U.S. registered voters. Okay, what is it that we want to know about these registered voters in the U.S., right? We're trying to predict who's going to vote for Hillary. So here we're saying that the parameter, remember that that's the P, we're looking at the proportion of our population, so of U.S. registered voters who will vote for Hillary Clinton. So I'll leave that as HC. Okay. Our sample, who do we actually have information from? We have information from the 1,000 registered voters that we were able to contact by phone. So our sample is the 1,000 U.S. registered voters. So again, even if I set out to get information from 2,000 individuals, right, it's only those that I actually have information from that make up my sample. So my sample is only the 1,000 who we got information from. Okay, and our statistic, what is it that we know about our sample? Here's my little P hat for my statistic. Well, we know that 600 out of 1,000 of them, or 60% of them, plan to vote for Hillary. So 60% of registered voters plan on voting for Hillary. Okay, so during election time, we hear all sorts of information about predictions about who's going to win, what's the margin of error. So here is a nice place just to show you some real-world application. All right, so now we're extending this to a sampling distribution model. So the model shows the behavior of the statistic, the sample proportion, over all possible sample sizes, and our sample size is n. So it follows a normal model if the following three conditions are met. So let me go over that here. So here again, I just want to stress, model shows the behavior of the statistic, the sample proportion over all possible sample sizes of n, follows a normal model if we can meet these conditions. So what we're saying is, well, really, if we have here, if we've collected a lot of data, we have a lot of statistics, we're going to expect that our true parameter should fall right smack in the middle. And that's what we're trying to predict. That's what we're trying to estimate. So I'm just helping you to visualize, right? We have a lot of statistics. When we concentrate them, draw in that density curve over them, this is what we would expect it to look like, and our true parameter should fall right smack in the middle of that normal curve, but only if these conditions are met. So first we have to have some component of randomization. So our sample should be an SRS of the population. We know that every individual should have the same opportunity, the same chance to be picked as part of the sample. So here I'm just going to write should be an SRS, right? We know that that means that every individual has the same chance to be picked as part of the sample. So every individual in our larger population has that same opportunity, the same chance to be picked as part of the sample. Okay, the 10% condition is saying, well, our sample size, it really should be no larger than 10% of the population. So that just means that it should be less than 10% of the population. Okay, and this condition really, it's tied to independence. We want to make sure that we don't have too big of a sample size where one outcome could influence another. Okay, success failure. So we want to make sure that our sample size is big enough so that both the number of successes and the number of failures are at least 10. So sample size has to be big enough so that n times p, so the number of successes, so here is our sample size times here, the proportion of success has to be greater than or equal to 10. And same with the failures. So NQ has to be greater than or equal to 10 also. So again, it's saying that the number of successes, NP, and the number of failures, NQ, have to be at least 10, right? Greater than or equal to 10. Just write at least 10 off to the side like that. So what's funny about these two is that what it's really saying is that little quote I have at the bottom, well, we want it to be big enough, but not too big, right? So we're kind of balancing between these two because we want our distribution to appear to be normal, and we want to make sure that one outcome is not influencing the next. So our assumptions, our conditions to be able to use the normal model, right, has to be random. We have to have less than 10% of our population, and our sample size has to be big enough so that the count of success, NP, and the count of failure, NQ, have to be at least 10. All right, so then when we're getting our mean and our standard deviation, well, let me just go back to here. So if I was looking at, all these conditions are met, and I'm looking at my distribution of all these different statistics, where would the mean fall? What would be the expected value? Well, I'm expecting it to be here, the true proportion is really the same as the average of all of the statistics. It should be right smack in the middle. So here we're going to say that the mean, or again, we call that also expected value. Our mean of all of our statistics, or our sample proportions, should be equal to that true parameter, the true population parameter. Okay, and then our standard deviation, and this is a formula that I will give to you. Our standard deviation of all of these statistics should be equal to the square root of PQ over N. So just like I've been giving you a little cheat sheet on recent quizzes, you will get these on your upcoming quizzes as well. I don't need you to memorize it. I don't need you to memorize the standard deviation here. So again, square root of PQ over N. And here, just to visualize it here, if I build a normal distribution, here's my normal curve. Here is my mean, right smack in the middle, right? That's the true parameter. And then here we're just looking at one standard deviation above, two above, three above, one below, two below, three below, just like that. All right, let's flip to the second page. Okay, suppose that 26% of all high school students at a large school spend about half or more of their earnings on a car. So here, just know that 26%, what is that figure? Well, it's saying 26% of all high school students at a large school spend about half or more of their savings on a car. So that number right there that it's giving us, it's talking about everyone. So it's giving us P, it's giving us the population parameter. Okay. A random sample of 150 students, so we love that it says random, and we're told 150 students from this school are surveyed. Let P hat, the statistic, represent the proportion of students in the sample who spend about half or more of their earnings on a car. So calculate and interpret the mean and the standard deviation. Okay, so first remember that the mean of all of our statistics is going to equal what the true population parameter really is. So in this case then, our mean will be 0.26. Right? We expect the proportion of students who spend half or more on a car will be about 26%. Okay, standard deviation. So standard deviation is equal to square root of PQ over N. So just reminding you of the formula that was on the other sheet. And then when I plug in, so my standard deviation, big square root, 0.26 times its complement, so 0.74. So P times Q, and then divided by 150. Okay, so let me type that in. So I have 0.26 times 0.74 divided by 150, and then I take the square root. So I get about 0.0358. So my standard deviation will be about 0.0358. I'm just keeping everything in decimal right now. Okay, if you left it as a percentage, that would be perfectly fine. All right, so then let me kind of summarize that. So if we have SRSs of size 150, so assuming we're looking at SRSs of size 150. The proportion of students who spend, half or more on their car will typically vary by about 0.0358 of the true population proportion of 0.26. Okay, so again, I'm just writing that as a statement. So I'm saying in SRSs of size 150, the proportion of students who spend half or more money on a car, we expect it to vary by about 0.0358 of the true population proportion of 0.26. Okay, and I just want to remind you that P, our population parameter, sometimes we call it population proportion, and P hat, our statistic, sometimes we call it the sample proportion. It means the same thing. All right, move on to the next one. To audit one department of a large corporation, an accountant selects a random sample of 80 transactions. Historically, the true proportion of transactions that are more than 1,000 is 0.42. Would it be appropriate to use a normal distribution to model the sampling distribution? Check the three assumptions. So here, just tracing back through it, it says the word random. I love it. And then I'm seeing sample of size 80, so that's my N value right there. Okay, we're told that historically the true proportion of transactions that are more than 1,000 is 0.42, so it's giving us the true parameter right there, the population parameter or the population proportion, right? That's the same thing. So would it be appropriate to use a normal model? So the three assumptions. So first, do we have randomization? And we can give that a big check. We're told that language right here where it says random sample. Okay, the 10% condition, let's check that one. So here, is it explicitly telling us? Well, no, it's not explicitly telling us anything, but we need to see if we can kind of just assume that our sample size would be less than 10% of our population. So in this context, do we think that 80 transactions would be less than 10% of the total transactions for a large corporation? And if we're going to say, yeah, that seems reasonable, then we can check this off. So again, let me just write down what it's saying first. Our sample size has to be less than 10% of the population. So again, in this context, we're saying, well, yeah, I think that 80 transactions should be way less than 10% of the total transactions for a large corporation. Okay, great. Second condition is met. Third one, we're looking at the success-failure condition. Okay, so here we know that the N value is 80. P would be 0.42. So then failure Q would be its complement, 0.58. Great. So n times p, is that greater than or equal to 10? How about n times q? So if I plug in 80 times 0.42, I'm going to get 33.6. So, yep, in the clear. And then if I look at the failures, so 80 times 0.58, I get 46.4. So, yep, I am in the clear. So we want to make sure that we have enough successes and we have enough failures. So all three of our conditions have been met. So we can say, yes, proceed. The sampling distribution is approximately normal. All right, and then that's it. That's all I'm looking for. I want to see that requisite work, and I want to see that final sentence as well. All right, last up, one more, trying to pull it all together. Okay, in a recent year, a fact sheet for the state of Pennsylvania stated that 72.6% of all public high school seniors were planning on going to college that next year. So it's giving me the true parameter, P. An SRS, right? Love seeing that word because then I know that my randomization assumption is met, of 400 public high school seniors, so there's my N value of 400, were surveyed. Calculate the mean and standard deviation, check the three assumptions. Then, this is our last step, find the probability that the sample proportion who are going to college next year will be within 3% of the true value. Okay, so let's do the first part. So I'm looking at my mean, and that was given to me right here. So I'm going to keep everything as a decimal, so 0.726. If you wrote it as a percent, again, not a problem. So here, this is the proportion that we would expect to be going to college. Okay, our standard deviation next. So square root of P, 0.726. Q would be its complement, so 0.274. And then divide it by the sample size of 400. So when you crunch that, we get about 0.0223. So our standard deviation will be about 0.0223. Okay, check the three assumptions. So randomization, is randomization met? Check, right? We saw that language of SRS. We love it. Okay, second, 10% condition. So is it safe to assume that our sample size is less than 10% of our total population? And I would say, well, yeah, absolutely. 400 high school students has got to be way dramatically less than the total students in the state of Pennsylvania. So I'm going to say, yes, absolutely, but let me just write down what I said. So sample size has to be less than 10% of the population. So 400 high school students is way less than the total students in Pennsylvania. I'm just going to abbreviate. Okay. And then lastly, I'm looking at the success failure condition. So I know that N is 400, P is 0.726, and Q is 0.274. So I want to make sure that I have more, or at least, so it could be exactly 10 or more, at least 10 successes and at least 10 failures. So if I do 0.726 times 400, That's going to get me 290.4, so absolutely I'm meeting that criteria. And then 0.274 times 400, I get 109.6, so boom, check, I'm meeting that criteria too. So again, these two, right, we want it to be big enough, but not too big. We want to make sure that it would look like a normal distribution. So right now we can say, yes, we have met all three assumptions. Now we can move forward and finish up the problem. We know that our sampling distribution is approximately normal. So now the last part of the problem is saying, find the probability that the sample proportion will be within 3% of the true value. So let me make a visual. So here is my normal curve. Right smack in the middle of it is my mean, which is 0.726, right? That's my p-value right there. Okay, and then here we could convert to z-scores, but I'm going to show you another trick where you actually don't have to. You can go off of the raw data. So here what I'm going to do is I'm going to look at what is my standard deviation. Okay, so my standard deviation right here is 0.0223, and I know that I'm looking at within 3% of the true value. So what I need to actually get right now is I need to look at that 3% and make certain markers, because I need to build with my mean and standard deviation to find the proportion that would fall within those markers. Okay, so right now I'm going to look at here my mean, and I'm going to do plus or minus that 3% value. So I'm going to do 0.726 plus or minus 0.03. So that's going to give me 0.696 to 0.756. So I'm looking roughly here and here. All right, so again, just to make sure that we're super clear, right here is the 72.6% of all public high school seniors who plan on going to college. So we're looking at building here plus 3%, minus 3%. I'm just writing it as decimal forms because I want to be within 3% of that true value. And I'm interested in within, so I'm interested in what is the likelihood, what is the probability that I'm in this window from here to here, this spread of values. So typically we've converted to z-scores and then gone to normal CDF in the calculator. We could still convert to z-scores, but we can also build off the raw data too. So to remind you, when we do normal CDF, we always plug in that lower boundary, the upper boundary, the mean, and the standard deviation. So if I want to use my raw data here, I need to build off of my mean and my standard deviation, and I need to tell it the lower and upper boundaries. So my lower boundary, so I'm going to do normal CDF, my lower boundary will be 0.696. My upper boundary would be 0.756, and then my mean is 0.726, and my standard deviation is 0.0223. So if I had converted to z-scores first, which again would be perfectly fine, it's just now an unnecessary step. I'm going to let us go through raw data now. So lower boundary, upper boundary. Mean, standard deviation, let's crunch. So here I'm going to normal CDF, and I'm entering my markers. So lower boundary, 0.696, upper boundary, 0.756, mean of 0.726, standard deviation of 0.0223. Okay, so let me just skim through here. So 0.696, 0.5, yep, okay, looks good. So I'm gonna hit enter and I'm gonna get about 0.821469. So as a percent, that'd be 82.1469%. So we'd say that about 82.1469% of students in the state of Pennsylvania should be within 3% of the true value, which was 72.6% going to college the next year. All right, so today was my first layer of our new skill. I will circle back tomorrow and do the second layer of it, and then we'll review for our quiz that's coming up pretty soon. Okay, but we have a little bit more time to work with our latest topic, sampling distribution of sample proportions. And I want to make sure that it all sinks in. If you guys have any questions, please make sure that you reach out. All right, have a good rest of your day.